Okay, that's Farrell.
Great, thank you very much for coming, and thanks for the opportunity to present at this extraordinary not a Wednesday seminar. So I'd like to talk today about a solver for a really difficult equation, for the Navier-Stokes equations. And because I appreciate that while there are world experts in solvers here, there are also people who mainly focus on geometric numerical integration. So I'll try to take it slow, and maybe the experts in the audience can press me afterwards. So what's the problem that I'd like to solve? Well, I'd like to solve the fundamental problem in incompressible fluid mechanics, the stationary Navier-Stokes equations. So I'm looking for a velocity and a pressure in vector h1 and scalar L2 that satisfies this equation. So this is the momentum equation. This is the viscous term. This is the advection term. This is the pressure gradient. Okay, I want to solve that subject to the constraint that U must be incompressible, that the divergence of U must be 0. And this constraint is always somehow the headache in this equation. And the running theme of this talk will be that in order to solve this efficiently, you need to really understand what the kernel of the divergence is, right? Going back to results by Jinchao and Joachim Schöberl and others. So what will I present today? I'm going to present a preconditioner for this equation, for the Newton linearization of this equation, with the following property, that the performance is going to be robust with respect to this parameter, the viscosity. So if you like, you can think about the viscosity as 1 over the Reynolds numbers, so I'm interested in low viscosities or in high Reynolds numbers. For me, this is because I'm interested in bifurcation analysis. I'm interested in computing the multiple stationary solutions of this equation. But if you're interested, for example, in fully implicit discretizations, then you would also get a problem like this. And almost everything about this equation breaks down as you go to lower viscosities, as you go to higher Reynolds numbers. So you lose uniqueness of solutions, you get boundary layers. If you're naive about your discretization, your error estimates break down. But here we're going to achieve a solver algorithm that's robust with respect to this viscosity. And this is a complicated problem, and there's going to be many moves of the following form, where we're faced with problem X, so then I do something to fix problem X, but then that causes problem Y for me instead, and then I have to go do something about problem Y. So there's never sort of a free lunch. There'll be lots of shifting, workaround, and difficulty around to different problems, but ultimately we can deal with them all. So sort of the moves in the game are that we're going to do a block preconditioner. I'll explain what that is. And we're going to have an augmented Lagrangian term to give us control over something called the Schur complement. That's going to make this momentum equation even harder to solve. So we're going to have to do a non-nested multigrid scheme for this with with a multigrid relaxation that captures the kernel of the divergence, prolongation operators that involve local solves, all sorts of stuff. Okay, so what's the big picture of how the solver works? So let's suppose that I've discretized. I'm going to talk about the finite element discretization in a little bit, but let's postpone that for now. And then I've done a Newton linearization in order to solve this problem by solving a sequence of linear problems. Okay, so I have linear systems of this form to solve. Okay, so this is the momentum operator with the viscous and the 2 advection terms coming from the linearization of that quadratic advection term. This is the pressure gradient. That's the divergence operator. Okay, and so I'm in Oxford, and a few doors down the hall from me is Andy Wathen. So of course we have to use Andy Wathen's block preconditioning viewpoint framework is his world. So the key idea is this. If you have a block structured matrix like this, you can do a block Gaussian elimination, and you can write formally its inverse as the product of these 3 matrices. You haven't done any work yet, you've just done some calculations on paper. But what this lets you do is, if you have good solvers for this guy, so the 1-1 block, the top left block that showed up in your problem, and this new operator, this Schur complement, if I had good solvers for those, then I could plug them into this formula. I've got a formula for the inverse of the matrix, and then I've got the problem solved. Okay, so that's the game. I'm going to use approximate solvers for these 2 guys, and that'll give me a preconditioner for J. What is this Schur complement? This is really where all the difficulty in this approach lies, because this A, that's a discretization of a differential operator. It's sparse. We can look at it, we can understand it, but this Schur complement is more difficult. What is it? It's minus B A inverse B transpose. And in particular, A is elliptic, right? Or A is sparse, but its inverse is dense. And so this S is dense. So I'm never going to be able to assemble this matrix. I'm never going to have it in front of me in memory. So I have to do something matrix-free for this. And moreover, every iteration of a Krylov method will require solution of a linear system with me, right? So I really want to minimize the work that I'm doing there. So I really need to understand what the Schur complement is. And so in this viewpoint, in this world, the aim of the game has become to find fast approximations to solve the top left block and to solve this Schur complement.
So these fast approximations will help you design a preconditioner, not the solver itself.
So if I really solve these systems to machine precision, then this would give me the inverse in three matrix vector products, right? Or multiplying by these matrices. In practice, I'm not going to solve them exactly. I'm going to do them inexactly, and then I have a
So you
method
have a
on the
J tilde
outside.
and inverse, and then you use that as a preconditioner.
Yeah, exactly. But I have a good approximation to J. Okay, so where did this come about? Well, really, the first success of this block preconditioning approach was in Stokes. So Andy in the 90s was thinking about how to solve Stokes, where you lose the advection terms. And what did he say, along with David Sylvester, is that you should use multigrid for the inverse of the top left block. And then, of course, the hard part is the Schur complement, but he can prove that in Stokes, the Schur complement is spectrally equivalent to, so it's like, in some concrete sense, the pressure mass matrix. So this is a nice operator. It's the discretization of the identity on L2. It's really easy to solve, right? So I can build preconditioners from this, and that gives you a good preconditioner for the Schur complement. Okay? So that works very nicely for Stokes. So you can try the same strategy for Navier-Stokes, and it turns out that it works up to about Reynolds number 10. So only for very, very limited range of viscosities. This doesn't work at all for many problems of interest. So then they went back to the drawing board and they thought, well, really the problem is we're losing control of the Schur complement because you've got the advection terms inside the A inverse in there. That's what's going wrong. And so the game became to try to have better approximations of the Schur complement. So probably the most computationally successful is this PCD strategy, this pressure convection diffusion, where they approximate the Schur complement with operators like convection diffusion operators on the pressure space. It works okay. It works up to maybe Reynolds numbers in the low hundreds. You can question the basis of it. You know, for example, the pressure space is only L2. What does it mean to solve a convection diffusion equation on this space? But so the theory is weak, but it's effective for the low hundreds. So but what I'm going to show is several orders of magnitude beyond this. I'm going to show results that are robust up to Reynolds number 10,000. So I was trying to do some bifurcation analysis of problems with fluid mechanics. I was in Simon Taverner's office, whom I believe was a colleague of both of yours, right? And I was looking for good solvers for the Navier-Stokes, and I came across this paper by Benzi and Olshanskii, and they say rather casually that, oh, we have a solver that's mesh independent and it's also robust with respect to the viscosity. I was amazed that this was possible. I hadn't heard about this before. This was maybe 2 years ago. And so I was really excited by this, and I emailed Michele and Maxim and I said, could I, is it implemented anywhere? Could I take a look? And they said, no, we implemented it for the paper, but that code is long dead. Eventually, a few months later, Maxim went, I believe, back to his cabin in Russia and found his old laptop that he had worked on this paper, and he emailed me the code from that. But that was sort of the state. So what's the status of this work? It's a superb contribution, really amazing. But there are some problems. So there's no implementations, and the reason is because the scheme is very difficult. Right? No one implemented it since the paper was written. And it was only implemented in 2D for one very specific discretization. In particular, a discretization that blows up as you increase the Reynolds number. So whose error estimates decay as you increase the Reynolds number. So while you could compute the linear systems efficiently, actually what you were computing maybe wasn't so good. Okay, so that's where we take up the story. So before I get into the solver, I have to tell you about what discretization I use. And of course, we're here at a structure preserving discretizations workshop, so the discretization that I favor is going to be structure preserving. But I'll also talk about a non-structure preserving discretization in order to illustrate the differences in how you might approach solving it and indeed what can go wrong. Okay, so I'm going to consider these two discretizations. So this low order one, so it's not exactly the same as what Benzi and Olshanskii considered, but it's close. So this, if you're not familiar with this finite element notation, let me just briefly explain. This is the element I use for the velocity. This is the element I use for the pressure. So this is a continuous piecewise polynomial representation for the velocity that's quadratic on every cell, and this is a discontinuous representation of the pressure that's piecewise constant. Here, and then it turns out that the natural 3D generalization of this is very expensive. So this element is insubstable in 2D, but not in 3D. So if you want a stable discretization, you would probably go to CG3 DG0. But that's very expensive. You're using cubic polynomials, but you're only getting a very low order of accuracy because you're limited by the approximation of the pressure, this piecewise constant approximation of the pressure. So maybe a better thing to do is to use CG1 augmented with these facet bubbles on the surface, so you have extra degrees of freedom on the facets, so that you still have insubstability, but you also, it's not too expensive. So this is the low order discretization that if I refer to it. And this is the structure preserving discretization, this high order discretization I might refer to it. I might also sometimes refer to it as Skoffic alias, but I believe that Doug doesn't this terminology. So what's the difference? Here, so let's compare these two. I'm going to use the same element for the velocity, piecewise quadratic continuous polynomials, but now I'll use something different for the pressure. Instead of using piecewise constants, I'll use discontinuous piecewise linears. And why is this structure preserving? Well, the key relationship in this equation is that the divergence of u equals 0. And if you think about the divergence operator, it maps h1 into L2. It maps the velocity space into the pressure space. If you make this choice, then you inherit that structure. The divergence of something in this, well, I'm going to reduce the polynomial degree by 1, and I'll reduce the continuity by 1, and so I'll get something like that. Right?
Now you have me confused. You draw a picture that looks like continuous P1, but you're saying it's discontinuous. For the
Sorry, the dark green means discontinuous.
Oh, not where you put the dots.
Yeah, sorry. I took these from the Phoenix book, and I was thinking yesterday, oh, I should put them in here, but I didn't. Yeah, but this is discontinuous, I emphasize.
So this is an unstable element, right?
Well, I'll talk about that in a second. Yes. Well, your PhD student knows all about this. So, well, I'll defer that for 2 slides, but why might you want to use such a scheme like this? Well, here's the advantage, here's the upside of this structure-preserving discretization. So, let's just go and do the error estimate or the error analysis for Stokes. Forget about the advection terms because they complicate things. So this is from Boker-Young's Simon review paper a few years ago. This is our discretization error. This term is nice. This is something like a best approximation in my polynomial space up to some constant, right? So this is some quasi-optimality result. I like that very much. But this term I don't like. So this involves the approximation of the pressure, but it's multiplied by 1 over the viscosity. So as I reduce the viscosity, this estimate is blowing up. Right? And so we can see this in the computations. So now the estimate is for Stokes, the computations are Navier-Stokes. So here's what I do. I'll solve the problem, I'll fix a velocity field, right? So I'll fix the problem. I'll fix the solution at least. And then I'll solve it for varying Reynolds numbers. And then I'll look at the convergence as I refine the grid. And if I use this low order discretization, they're all converging at the expected order, but the curve is getting worse as I increase the Reynolds number, right? These blue lines aren't on top of each other. It's getting worse as I increase the Reynolds number. But for the structure preserving discretization, this term vanishes. So my error estimate isn't dependent on the viscosity anymore. And indeed you can see that the corresponding error curves for the structure preserving discretization give you very nice Reynolds-robust convergence. So that's an important ingredient. So that's why you might want to use such a discretization. And I should say that there are other structure preserving discretizations. It's a big field now, and indeed Professor Zhu knows all about them. Has published lots of papers. But I'll talk about this. So, but why has this not taken over the world? What's the downside of this approach? The catch is that this discretization isn't stable on arbitrary meshes, as Doug just pointed out. So this discretization, it's great when it works, but you can give me a mesh, a pretty mild mesh, and it will fail on that. And so one response might be to introduce some extra structure in our mesh. So this was studied by a PhD student of Doug's in the 90s. In the 2D case, I believe, and then the 3D case was proven later, where they do the following. If you can give me any mesh that you like of your geometry, and I'm just going to introduce a little bit of extra structure, and then that will guarantee stability. And what is that extra structure? It's to do a barycentric refinement. So on every cell of the input mesh, I introduce a vertex of the barycenter, and then join it up into the existing vertices. And that will guarantee stability. If I choose a polynomial degree here, k is the degree of the velocity element, big enough, equal or to or bigger than the dimension. Okay, so if I'm doing a multi-grid solver, here's how I build my hierarchy. You give me a mesh, and then I'll do a barycentric refinement in order to guarantee stability. Then, if I want to build a multi-grid hierarchy, I'll go back to the original mesh, do a uniform refinement, and then a barycentric refinement of that, and keep going like that. So these are the grids that I'll actually use in my multi-grid scheme. So this is nice because it guarantees stability. There's a catch though, which is that these meshes are not nested. Right? So there's a function I can have on this mesh that I can't represent exactly on that mesh. And now that's an example of me doing something to fix problem X that gives me problem Y later on, but we can deal with this. I'll tell you how to deal with this later. Okay, one last aspect of the discretization before I move on. So for the low order scheme, it's really crucial that you stabilize, that it's oscillatory at high Reynolds numbers. And so a popular stabilization scheme is the streamline upwind Petrov-Galerk. I won't talk about it too much, except to say that if you try this with the Schofield-Helios element, it's a disaster. And I don't really understand why, but even if you use LU, it becomes so nonlinear that you can't even solve it at Reynolds number 10. And I suspect the reason is that in the lower order case, this grad P on each cell is disappearing because P is a piecewise constant, but it's not in the higher order case. And so what that means is that now you've introduced this whopping great coupling between the velocity and the pressure. And so I suspect that extra nonlinearity gives you a headache. So if you want to stabilize the higher order scheme, you can argue about whether you need to or not, but if you want to stabilize the higher order scheme, a much better choice is the stabilization first studied by Douglas and DuPont in the 70s and then later on picked up by Berman and Hansbaugh, which is something of a flavor of an interior penalty stabilization, like a DG chain, where what we're doing is we penalize jumps in the normal component, we penalize jumps in the normal component of the gradient of the solution. So essentially you're trying to make the solution smooth, you're trying to penalize deviations from being C1. So this term is intriguing, actually. It'll play a key role in the story later on. That'll come in. Okay, so that's the discretization, discretizations that I'll consider. So now let's see how might we actually solve these problems. So here's what I'm going to do. The situation is as follows. I have the A solve and the S solve, right? And the A solve I know how to do, the S I don't. What I'm going to do is I'm going to add on a term to the equations that will give me complete control over the Schur complement over S, but at the cost of making A more difficult. I'm going to shift the difficulty from one part into another. And that term will be an augmented Lagrangian term. So let's just go back to Stokes for a moment. So Stokes you can write down as this optimization problem. Minimize this potential energy subject to the constraint that div B equals 0. And the standard approach is to introduce a Lagrange multiplier to enforce this constraint. That's the pressure. And then you take the optimality conditions, and there you go. There's Stokes. But another way that you might think about attacking this optimization problem is to penalize the constraint. Right? So I might say, I'll add this penalty parameter gamma over 2, and then take the L2 norm squared of the divergence of V. Right? And as I send gamma off to infinity, in order to minimize this penalized energy, I have to satisfy div V equals 0. Right? So that might be another way that I could do it. I could do a penalty approach. In this case, with the augmented Lagrangian, I'm going to do both. I'm going to have a pressure Lagrange multiplier, but I'm also going to add this term. And the reason for it is the following. So there's a lovely book in the 80s by Farrell and Benzi. They don't quite state it in these terms, but this is how I interpret it. That as you send this penalty parameter off to infinity, the Schur complement becomes easy, becomes nice. You gain complete control over what the Schur complement is. It approaches a scalar, a nice scalar, times our old friend the pressure mass matrix, something that we can solve very, very easily. And why is that? And morally speaking, you can think of it like this. As I send the penalty parameter larger and larger, this term is taking more and more of the burden of enforcing the constraint. So the Lagrange multiplier doesn't have to do anything. And that makes the Schur complement nice. That's a little hand wavy. We can be a bit more direct if we think of, there's one other thing I should say. So when you take the optimality conditions and integrate by parts, what does this do to your equation? It adds this term here, minus gamma, the gradient of the divergence of U. So this is the term that if we add it, will give us control over the Schur complement, but it's going to make solving the momentum equation much harder. We can also see this on the discrete level if we choose to. So let's look at the linear system that we have to solve. This A, B transpose B. what I can do is I can add on this term here, gamma B transpose Q inverse B. And that doesn't change the solution of this linear system at all, because the second equation says that B times U equals 0, and as soon as this B hits that U, it'll be 0, right? So that it doesn't change the solution one bit. But you can work out, and this is an explicit equals, that the Schur complement of this new system, you apply the Sherman-Morrison formula, it's equal to the Schur complement of the old system minus gamma Q inverse. So as I send gamma very large, I can approximate this guy with this guy and forget about this term. And so for the low order case, we think about it in this way. And so what's the difference? The difference is that you can think of B as the divergence operator, but this Q inverse means project onto the pressure space. That's what the pressure mass matrix does for you. So this isn't the divergence, it's the projected divergence, the discrete divergence. And that'll be important later. But for high order, they coincide because, of course, the divergence of the velocity space is the pressure space, so the projection onto the pressure space is that of identity. Okay, so what's the good news? If you take this strategy, if you add on minus gamma grad div u to your Navier-Stokes equations, what happens is that your preconditioner becomes great, right? So let's use a direct solver for this augmented momentum operator for the A, and let's use a pressure mass matrix for the S, and let's plug it into our preconditioner that we had at the start. And as I increase gamma, these numbers approach 1. And in fact, if I took one more order of magnitude, it would be 1. Okay? So this gives me complete control over the Schur complement. The downside is that I've shifted all the difficulty into solving this momentum equation. In fact, this has become a nearly singular system of the kind that Professor Zhu spoke about yesterday. And so I've shifted all the difficulty into this. So if I do something naive, if I just use out of the box AMG, for example, for the 1-1 block, which I have to do something better than a direct factorization if I want to scale, then as I increase gamma, my preconditioner breaks down because AMG isn't able to solve this linear system for reasons that I'll explain. So now the game has become, can we build a solver for this augmented momentum equation? If we can solve the Navier-Stokes. Okay, so how do we solve the augmented momentum equation? So this now deeply relies on theory of space decomposition, subspace correction methods, and so on, pioneered. Okay, so let's ignore advection. So I don't know how to deal with the advection terms in the analysis, and I dearly love to hear if someone does have an idea. So let's ignore advection, and let's just think about what the bilinear form corresponding to this matrix is. So we have two terms. We have the viscous term. So here we have the inner product of the symmetric gradient of U, the symmetric gradient of V. And then, so this is nice, it's symmetric and it's coercive, so long as I have the right boundary conditions, right? So this is a lovely term, can't complain. But this term is the form that gives you this matrix here, and it's the inner product of the projected divergence of U, projected onto the pressure space, and the projected divergence of U. And why does this break down? Why does my solver break down as I send gamma large? Well, it's because this term has a very large kernel, right? This is symmetric, but it's only semi-coercive, it's positive semi-definite. And the reason for this is because you can give me any function that has divergence U or projected divergence U equals 0, and it disappears. So as I send gamma large, we're approaching an equation that's singular, and so this is a nearly singular system, so we need to deal with that. So how do we do it? Well, we're going to build a multigrid scheme for this problem, and multigrid has two main components. You have a relaxation that you do on every level, and you have intergrid transfer operators. And in order to have a scheme that's robust with respect to these two parameters, the viscosity and the stabilization, we need to have both of these components be robust. We need to have a robust relaxation, we need to have a robust transfer operator. I'll talk about both of those now. So for the first case, the robust relaxation, we need a simple iterative method that we can apply on every level of our multigrid hierarchy that will deal with the error nicely, and it won't break down as I vary the coefficients. How can we achieve that? So let's take a look at an abstract result, a simplified abstract result. So let's consider the following variational problem. For positive constants alpha and beta, I want to find a solution in some finite dimensional Hilbert space, V, such that this holds, where this guy, A, is a nice term, it's symmetric and coercive, and this term, B, is symmetric, but it's only semi-coercive, it has a kernel. Right? And the problem will be trying to understand what the kernel of this B is, trying to capture through the kernel of V. Okay, and the way that I think about the relaxation methods is from the viewpoint of Professor Zhu, these space decompositions or subspace corrections. So what I do is I take my vector space of solutions and I break it down into a bunch of smaller spaces. So you can think of these VIs as being functions that are supported on parts of the domain. So for example, I could do you know where the chalk?
Go down, go down.
Oh. So for example, if I had a domain, and V is the functions that are supported on this domain, then I could draw a line in the middle, and then I could say that all the functions that are supported on this part, that's V1, and all the functions that are supported on that part, that's V2. And so in order to have one of these space decompositions, what I must be able to do is you can challenge me with the function in V, and I must be able to write it as the sum of functions in the smaller spaces. Of course, it doesn't have to be unique. Where those deep domains overlapped, I have a non-unique choice. But just so long as there is a choice to make, then I can write this. It doesn't have to be a direct sum. And so what does the algorithm involve? Well, once you have a space decomposition, what you can do is you can approximate the error by solving the error equation inside each subspace in turn. And then you combine all of those estimates for the error together to give you a correction. Okay, so a space decomposition induces a numerical method, induces a relaxation scheme. So as a concrete example, if you take each VI to be the span of a single basis function, so this is a span of a bunch of basis functions, and I can say each VI is the span of a single basis function, then that gives you Jacobi if you do it additively, or Gauss-Seidel if you do it multiplicatively. Okay, but the reason to write it in this way is because the criterion for what makes a robust relaxation scheme is best stated in this form, not in Lagrangian, in terms of functional analysis. So here's the result. So this summarizes maybe a bit too much the results by Joachim Schöberl in the 90s and Professor Zhu and co-authors a little bit later on. And so what do? So we define the kernel of this semi-coercive term. So these are all the functions that have divergence 0 in our case. So it's all the functions that I can plug in the first slot so that when I test them against the test functions, that's equal to 0. And what do I need for my space decomposition? I need my space decomposition to satisfy the following property, this equation here. And if I satisfy that equation, I get robust convergence. I can vary the parameters, and the convergence doesn't change. And if I don't satisfy this, well, all the experiments at least suggest that you won't get robust convergence. So what is this criterion? What does it say? So remember that the space decomposition was, the game was, you can challenge me with the function in V, and I must be able to write it as the sum of functions in each of the VIs. Okay? So with this, there's another game. You challenge me with a kernel function, something that is divergent 0. And then I must be able to write that as the sum of functions in the small patches, the small subdomains, but I only get to pick kernel functions from each of the patches. So that's my restriction. Okay? And in particular, take Jacobi. If VI is the span of a single basis function, and that basis function isn't divergence-free, then this intersection is empty. Right? And so I have no hope of winning that game. I need to choose a different space decomposition. If you're a linear algebra guy, you can think about, you need to get the right blocks for your block Jacobi method. Some choices of blocks work, and some don't. So what's the right choice of blocks? Well, for the low order case, for the CG2 DG0, Joachim Schöberl proves in the 90s in his PhD thesis that the right space decomposition is this one. So what do? I call this the star patch, the star around the vertex. That's the word from algebraic topology for the construction we're about to make. So what do? You loop over all of the vertices in turn, and then you gather all the cells connected to that vertex, and then you look at all the degrees of freedom inside that patch, but not the ones on the boundary. Okay, I'm opposing homogeneous Dirichlet conditions on the boundary. So in particular, for the patch around this vertex, it gathers these guys. And then I do the same for the next vertex. That gathers this patch, and of course they overlap, but that's fine, no big deal. Okay? And you do that for all the vertices in the grid. And it turns out that that is the right thing to do for this kernel of the divergence, this projection onto the piecewise constants of the divergence. And I should say, so this is the exact same patch that's used in Arnold Fokker-Winther for robust multigrid and HDiv and HCurl. Okay, so that's the low order case. What about the high order case? So remember, we had to introduce this macro element structure in order to stabilize our scheme. It'll turn out that that'll be important. It'll actually give us a nice relaxation. So here now, we're not interested in the the kernel of the projection of div, because the projection is the identity. We're just interested in what the kernel of the divergence is. And the way that we can understand that is through the study of an appropriate complex, an appropriate Hilbert complex. So for example, we might consider the Stokes complex. So what is that? You start with constant functions, and then you embed them into functions over the domain, and those are in H2. I can differentiate it twice. Okay, that's fine. I can take a H2 function, and I can differentiate it, and it gets me into this funny space you may not have heard. The vector fields that are H1, whose curl is also in H1. Okay, that's fine. I can take a function in this space, and if I take its curl, by definition, it's in H1. If I take a function in H1, its divergence is in L2. Great. And what makes this more than a bunch of Sobolev spaces with mappings in between, as of course is well known to many of you, is that the composition of any of the two of these operators is 0. Right? So if I take the gradient of a constant, that's 0. If I take the curl of a gradient, that's 0. If I take the divergence of a curl, that's 0. And by studying this complex, well, you can study the topology of the domain, but in particular, on a simply connected domain, this complex is exact. So the kernel of div is exactly the range of curl, at least on a simply connected domain. And so what does that mean? Well, we're interested, so this is our space for the velocity. So we have a finite element living below this, and this is our space for the pressure. We have a finite element living below this. But now all of a sudden we've become interested in what's the finite element for the space to the left? Because now I want to understand a basis for the potential space, right? For what the part that gives me divergence-free functions. So if we can find an exact subcomplex of this complex, then we know that we have a local basis for the kernel of the divergence, and that'll tell us what relaxation to use. So let's do an example. So let's look at 2D because it's easier to draw. So in 2D, we have H2 going into H1, going into L2. And these are the finite elements for the subcomplex that we're using to discretize the problem. I have a barycentric refinement. I'm doing, let's say, CG2 for the velocity, DG1. I did draw them in here, in the interior for the pressure on this slide. But there's another element lurking around. We don't use it in the computations, but it's there in the theory, which is the element for the H2 conforming space. And this is exactly the HCT element that conforms to H2 functions. But it's piecewise cubic, right? But only on a barycentric refinement. Right? So it's interesting that the barycentric refinement shows up here in another context. So in order to understand the kernel of div applied to this guy, I need to look at the basis functions for that guy. And where do the basis functions have support? Well, they have support in the star, but the star on the macro mesh, not on the mesh with the barycentric refinement. So if I have my grid, so the black lines were the cells before I did my barycentric refinement, and then the dashed lines are the barycentric refinement in the middle. And in order to capture the support of one of these basis functions, I need to take the star on the macro mesh, the macro star. So that's what this space decomposition looks like. I solve for all these degrees of freedom together at the same time, and do that for the next coarse vertex and so on. Okay, so that's the relaxation. There's one other key component of the solver, which is the intergrid transfer operators. So you need to make sure that if I solve for a coarse grid correction, that then when I transfer that up to a fine grid, I'm not blowing it up too much. The energy isn't being magnified arbitrarily. So I've got a coarse grid correction, and I'm mapping that to something on the fine grid with this prolongation operator. And what do I need? I need to control the energy norms of the fine guy in terms of the energy of the coarse guy. So this is the energy of the coarse guy, the viscous term and the divergence term. This is the energy of the fine guy, and I need to make sure that this energy is controlled by some constant times the coarse energy. And what can go wrong here? Well, imagine that we have a function on the coarse grid that's divergence-free, that's in the kernel. So that term has vanished. But now if I do a prolongation in such a way that it doesn't map into the kernel on the fine grid, then this term will be here. And now whatever divergence error I've made is multiplied by gamma. So that means that this continuity constant will have to depend on gamma. I can't make it independent of gamma. So in order to make it independent of gamma, you have to map kernel functions to kernel functions. And that's hard because our grids are nested. Right? That's where the non-nestedness of our hierarchy is coming to bite us. But the way that you can fix that, and I won't go into details, but you can achieve it by solving small Stokes problems over each course cell. So when I prolong, I have to do a local Stokes solve over each course cell. This isn't so bad because it's linear. You can factorize it once and save it and then just use it forevermore. So it's not so expensive, but you have to do it for it to work. Okay, and so that's the scheme in a nutshell. So what's the overall solver? So we're doing continuation in Reynolds number to get up to high Reynolds numbers. Then at each Reynolds number, I have a nonlinear problem to solve. So I'm doing Newton. Newton breaks down the problem into a sequence of linear systems. So I'm doing FGMRes for that. I'm using this full block inverse preconditioner, the three matrices that I showed at the start. For the Schur complement, I've got the pressure mass matrix inverse. And then for the augmented momentum operator, I have these ingredients. I've got a coarse grid solver that uses LU, a prolongation operator that transfers information between the grids that solves Stokes problems. And then for the relaxation, I do a few iterations of GMRes with this star or macrostar iteration as appropriate. Okay? And the hardest parts of the scheme are the local solves over the coarse cells and the star or macrostar iteration. But now we've implemented new solvers in Benzi that let you express these very, very nicely. So now we can build space decompositions from topological considerations very elegantly. Okay, so let me wrap up by showing some numerical results. Does it work? So here's a picture of a flow computed at Reynolds number 5000, but really the more interesting thing are the tables of results. Does it work? So what I'm showing here is the number of Krylov iterations per Newton step. That's the amount of work I have to do in my linear solver. I want that number to be 1. I want it to be low. I'm refining as I go down the way, and as I go across the way, I'm reporting on the solve at a particular Reynolds number. I'm doing continuation to get from left to right, but does the solver break down as I increase the Reynolds number? So if I'm constant as I go down the way, that's mesh independent, and if I'm constant as I go across the way, that's viscosity Reynolds-robust. And so we see here that actually we get very good results. So at Reynolds number 10, it takes 2.5 Krylov iterations per Newton step. At Reynolds number 10,000, it's only taking 8, right? Which is a very, very modest increase as you've gone through several orders of magnitude, keeping in mind that all the previous schemes would have broken down by this point. You wouldn't even be able to get to here. Okay? For the backwards facing step, it's even better. It barely increases as we go from low to high. If you look at the high order case, the Scott-Vigilius element, the structure preserving discretization, things aren't quite as good. I mean, they're fine, right? Going from 3 to 15 and multiplying by 5, that's okay. Certainly this is acceptable, but it's not ideal. Right? And so when I got these results, I said, maybe let me just try the next higher order scheme up. So this is the lowest order Scott-Vigilius, the one that uses CG2, DG1. What happens if we increase the polynomial degree by 1? All of a sudden, almost perfect robustness, vastly better results than there was before. No growth whatsoever for this problem with 10 million degrees of freedom from Reynolds number 10 to Reynolds number 10,000. Why is that? I'm not sure, but I believe it's because of the stabilization. So but let me report a funny observation. So you can give me a mesh, and I can solve the problem with velocity degree 2. And then I can solve the problem with velocity degree 3. A much finer discretization, many more degrees of freedom. But I can solve the problem with k equals 3 strictly faster than I can solve the problem with k equals 2, because these numbers are so much better than the ones in the previous table. Right? So that seems like a win-win. You get a better discretization and you can solve it more quickly.
These are both using Alfeld splits.
And I believe, this is a conjecture, but I believe that the reason is it's because of the stabilization. So remember, we have this stabilization term that controls the jumps in the normal component of the gradient. At high Reynolds number, this is doing something. This is acting. And what is the kernel of this? The message of the talk is you have to think about the kernel of your bilinear forms. What's the kernel of this? It's exactly the C1 functions. So we need a local basis for the C1 functions. When do we have a local basis for the C1 functions? Well, there's exactly a local basis for the C1 functions of degree 3, but not of degree 2 on these meshes, on this barocentric refinement. So I believe the reason why this works is because when you use CG3 for your velocity, you've got a local basis for the C1 subspace. And so your macro star relaxation is capturing that. And so you're robust not only to the stabilization, to the penalty term, but also to this parameter here. Okay, and you can do the same in 3 dimensions once you have the right software. And here the results are very nice. So I'll just highlight that here we have some simulations run with over 1 billion degrees of freedom, and we see almost perfect robustness as we go. In this case, up to Reynolds number 5,000, mainly because we ran out of time on the UK National Supercomputer. But I believe that if you kept going, it should work at least for a while. And same for the backward-facing step, with a problem with over 1 billion degrees of freedom, you have very nice control over the iteration counts. So we've really got the right idea. And the story is more or less the same for the high order case, so I won't dwell on it too much. Nice robustness. Okay, and so that's what I wanted to present. So let me just conclude. So we've developed a Reynolds-robust preconditioner for the stationary Navier-Stokes, both with Reynolds-robust error estimates and also Reynolds-robust preconditioning. And some questions for the audience and some remarks. So I think the biggest criticism that could be fairly made is that the advection terms were ignored in the analysis, right? We figured out what was the scheme we needed to do for Stokes with this augmented term, and then we did that, and it happened to work for Navier-Stokes as well. So can that be repaired? Can that be improved? So another important class of discretizations that enjoy this structure-preserving property are those that are HDiv conforming for the velocity. And so I expect that the same thing could be done in that world, and indeed I suspect that many of the ingredients will be simpler. You will need the prolongation operators, for example. And can these ideas of augmented Lagrangians plus kernel capturing multigrid apply to other problems? And with that, I'll conclude. Thanks very much.
Great, thank you for a lovely talk. Are there questions?
So how do you choose your beta and your gamma?
That's a good question. So the gamma, I choose to be the highest Reynolds number I'm going to target. So if I was going up to Reynolds number 10,000, I set the gamma to be 10,000 also. In some sense, there's something funny going on, because as you increase gamma, you're gaining better and better control over the Schur complement. And so long as you have a gamma robust solver for the top left block, there's sort of no downside almost. So you set it so that you're getting iteration counts that are almost 1. And then for the stabilization for the beta, that was done purely by experimentation. So we solved up to Reynolds number 10,000 with a bunch of different betas, and then looked at the pictures and said, oh, which ones are oscillatory and which ones aren't. So there's sort of an eyeball norm going on there. Maybe that could be improved.
So when you, go ahead.
So if you do this for the low Reynolds numbers, you have the traditional solvers. Can you compare the
Yeah. So the reviewers
accuracy?
actually asked us to do that when we submitted the manuscript in the low order case. And so we went and did the experiment. So we implemented another scheme called Simple, which is very popular in the engineering CFD community. And I'm very pleased to say that actually even at low Reynolds numbers, we're much faster than Simple, because so that they take many iterations. The iterations are much cheaper than ours, but because they're taking so many, that it ends up costing more in runtime. And we really did go all out and try to optimize the implementation of Simple. I think it's a fair comparison.
So the Alfeld splits. So when we did this with Jinshui Qin, I don't think we weren't recommending this particularly as a method. We thought this was interesting, that here's a class of meshes that it's stable on, but they're sort of ugly meshes with strange shaped triangles and stuff. But so how much does it cost? Have you done any sort of comparison between the best approximation with the best mesh, or a nice uniform mesh, as compared to what you add degrees of freedom when you go to this Alfeld splits? How does the approximation theory compare?
So we haven't done such experiments. In one way, it's, I've been waiting. So the way that we implemented the discretization of the alpha splits is really to introduce the split in the mesh, which isn't really the right way to do it. So this is sort of the first implementation. What we want to do is to put the macro element structure in the finite element library. So there's and then that the interior degrees of freedom will be statically condensed out. And then I expect that the extra cost of using the splits will be much less. And indeed, that lets us explore other macro-relevant structures. But no, because of this sort of, we're expecting that we'll replace the implementation with something else, I haven't done a time-for-time comparison.
I mean, you might take two viewpoints of it. One, you might say, well, the splits are there just for stabilization. They don't add too much to the approximation. You get as good approximation as you did with a mesh that you split. And so then all those interior degrees of freedom that you add are a result of stabilization, and you're paying for stabilization. We might take the other view, well, they're not such bad triangles. It's really like having an up.
Yeah, my view is much closer
I don't know where it fits.
My view, I haven't done the experiments, but my prior would be that it's much closer to the latter, right? Because, so we're not damaging the aspect ratios too much, and we're introducing extra degrees of freedom. And the original mesh is nested within the alpha split. So at the very least, your approximation error isn't getting any worse.
It's not getting any worse.
It may be getting worse in terms of the number of degrees of freedom, right? Or sort of the opportunity cost. But it doesn't seem so bad to me. The other thing I should say is that your students studied alpha splits for stabilizing the element, but it also has the surprising consequence that it gives you the local basis in the relaxation. It's because this element exists on the barocentric refinement that you get this nice local basis. So one thing that people might reasonably ask is, why don't you do one barocentric refinement to get stabilization, and then just do uniform refinement to build your multi-grid hierarchy forever after? And the reason is because your patches will need to get bigger and bigger and bigger. Right? You wouldn't get this local patch in your relaxation.
Well, okay.
So for the high Reynolds number, so you only use this penalization for the greater U times n. So there's nothing like augment or SUPG or that kind of stuff.
Yeah.
Can you explain why this should work?
So what happens at high
Because
Reynolds
this is a
numbers?
convection dominator.
Sure. In some ways, maybe you can think of this as a patch after the fact, rather than dealing with the problem directly that your Galerkin discretization is unstable.
You don't use SUPG.
No. But for the Schöberl case, we don't use the CPG. So what goes wrong? Experimentally, what goes wrong is that you see oscillations, grid scale oscillations in your velocity.
Do you see or you don't?
Well, if you don't stabilize,
You only stabilize along the normal direction.
well, so
That's not the streamline direction.
yes, that's right.
But
So-
usually you stabilize purely in the streamline direction, but you don't. Is
Yes.
any explanation for this?
So it's not changing the discretization to be a Petrov-Galerkin scheme. It's just experimentally fixing or computationally fixing what goes wrong with Galerkin schemes. So with Galerkin schemes, what happens is that you get these grid scale oscillations, and of course the tangential component of the gradient is already continuous, right? Because you had a C0 function. So the only sort of way that you can get these oscillations, the only way it's not smooth, is that you have these jumps in the normal component of the gradient. So that's why it penalizes the normal component of the gradient. But I mean, I should say that I'm not married to the stabilization. So this seemed like the most sensible option available to us at the time. I'm perfectly open to considering
Is
other
there a
schemes.
theoretical result for this
Yeah,
kind of
the-
scheme? Why this one is,
Yeah.
it's not a solver issue, it's discretization issue. Why this is stable? Anybody analyze it?
Yeah, so Eric Berman has several papers discussing this, both in the advection diffusion but also the Navier-Stokes case. So he has some nice papers discussing the analysis of this